So just a bit of motivation at the beginning. So air pollution remains one of the largest environmental health risks for people in the generally globally, but also in the EU. There are substantial costs associated to air pollution through the different health effects that it has. Air pollutants also contribute to climate change. For example, ozone is a greenhouse gas, and particles also have an effect on radiative forcing. So there's some win-wins there that are possible. In my work, I focus on urban areas, and urban areas are generally a focal point for both population as well as emissions, right? So you get this kind of like hotspot of both of these things, which results in a lot of exposure. And then traditionally, when we do air quality monitoring, you usually have a set number of locations in a city that make up a monitoring network. For example, in Berlin, there's about 4 million people, and we have 16 monitoring stations. And so you can imagine that over the broad scale of a city, with a limited number of monitoring stations, you're not necessarily going to be able to capture the complexity of exposure of the population. And so that's why we're starting to look at different ways and different instrumentation to be able to quantify air pollution and air pollution exposure. There were some recent revisions that, air quality directive in Europe. And as part of this, there's additional monitoring that's being required that will be implemented over the coming years, which I will touch on when I talk about the Net for Cities project that's related to these new and emerging pollutants, which basically means pollutants that don't have regulatory limit values because maybe the science isn't as advanced or established because maybe there isn't as much of a data basis. And the plot on the right basically just shows the status of monitoring locations within the EU in terms of achieving air quality limit values or guidelines. And so currently it seems like we're doing a really good job of meeting these limit values. But if you look at the middle plot, you can see that the future limit values, which were based on the revised WHO guidelines, plus a bunch of other political inputs, you can see that we're not doing as well, but it still seems not too bad. We're going to meet it in over half of the cases. But if you look at the WHO guidelines, which are basically just like the scientific basis and the levels that we understand would be necessary to reach to adequately protect human health, you can see that we have quite a long way to go. So if we think about urban areas, a lot of the statistics that I mentioned are focused at national or global level, but when we look at more local level, there are, in urban areas, you have a lot of differences in spatial distribution of air pollution, right? And so this shows an example of just two different environments in a big city, and how different exposure can be in these different environments. And a lot of the emissions in urban environments still do come from vehicles, especially for pollutants like NO2. And so this is basically where a lot of my research is aimed, is trying to better understand these very localized differences in urban areas to be able to understand what we need to do to reduce exposure more effectively, even as we seek to reduce pollution, air pollution overall. And so a lot of this is linked to urban planning and infrastructure and also related to transportation. In cities, air pollution or air quality is composed of various different sources, which also originate from different distances. And so the plot on the left here is showing kind of the different contributions, more from a spatial scale, I guess you could say. So you have a regional background contribution, which is air pollution that originates maybe nationally, like if we take Berlin as an example, and Germany or Europe or even further afield, so this long-term transport. You have the more local influence, so the city increment in the middle. And so this is generally emissions that are originating within the urban area. And then you have the street increment, or like the very hyperlocal increment, which is related to basically the exact location where you're standing or the monitoring was located, or the point that you're trying to analyze. And this can be then from anything from like emissions from a restaurant kitchen or a smoker that's standing next to you, or exhaust fumes if you're standing next to a road. And so the plot on the right shows just the breakdown of emissions in urban areas across Germany. And so this is specifically for NO2. And as you can see, you still have this very dominant fraction, about almost 2/3 from vehicles, from car traffic. You still have about 1/4, which is from long distance transport, so this regional increment, and then a number of other sources. So for other pollutants such as particulate matter, this would look very different, because particulate matter is not nearly as dominated by one source in the urban area. And then also, if you look nationally, this would also be different, because you have additional emissions in rural areas such as agriculture and things like that. So with that introduction, I'm going to talk a bit about the research approach that we use in my group, and then I'll talk about some of the sensor characterization work, the different policy evaluations that we've done, and then a bit about the Net for Cities project. So in terms of our research approach, my research group, our entry point is basically always related to the air pollution or the air quality aspect. We use the like constantly developing new generation of small sensors, sometimes also referred to as low-cost sensors, although there's kind of a gradient of those. And we try to do a characterization of these sensors to really understand their applications, the limitations in their applications, how we can generate robust data with these, to then also be able to effectively deploy these sensors in combination with reference instrumentation to be able to quantify changes in air quality and exposure related to mobility measures in urban infrastructure. We use a transdisciplinary approach, which I'm going to talk a little bit more about, which means that we're working in cooperation with local authorities and other stakeholders, basically partners outside of academia. And in a number of our projects, we also have an interdisciplinary approach where we're working with groups with different backgrounds to take like a more holistic evaluation approach to the implementation of some of these measures. So to just say a little bit about the transdisciplinary approach. So the idea with this is that we are trying to integrate our scientific research questions and our scientific interests with societal interests or societal problems. So in our case, it's bringing together research questions that we have related to urban air pollution, and talking with partners, for example, in the municipal government of Berlin, or also district governments of Berlin, or similar, for example, environment agencies or similar, and trying to integrate those in our research approach. So the idea, ideally, is that you start from the get-go integrating the perspectives of these different stakeholders in terms of already with the problem framing, and in that first phase. This does not mean compromising scientific research questions or anything like that. It's trying to find like where the synergies are, and can you consider other things to make the research more societally relevant or provide a different perspective, things like this. And then you go through the following phases in the same way that there is basically like a scientific process. There are also policy processes. And it's basically an integration of these two processes in their cycles. So then you go through and you do experiments and you do research and you discuss all of these results and approaches together. And then at the end, the results can then be integrated both in terms of the scientific context and the scientific community, and inform like further research, but also be useful for decision making and supporting policy. And so I'll come back to aspects of that at different points in the talk. Now I'm going to talk a little bit about some of the work that we've done on sensor characterization. So looking at these small sensors and how we can best use them. I've listed a couple of papers here. that highlights some of the work that we've done looking at small sensors and characterizing them. I'm mainly going to talk about the last one there, which is looking at the influence of temporal resolution on specifically NO2 sensor performance. I will mention the first one, which is this open source calibration methodology that Sean Schmitz published when he was doing his PhD with me. And the idea behind this is to provide a transparency in terms of how these small sensors, which usually work with, for example, like electrochemical sensors or metal oxide sensors or things like that, where you get a value like a voltage out that has to be then converted into concentrations, how that conversion is done, but also including steps like calculating error that is associated with these measurements, right? Because these small sensors, one of the disadvantages is usually that they have larger error, right? Which is associated to the fact that they are cheaper and widely available. So to talk a little bit now about the influence of temporal resolution. We did an experiment in the center of the city at a traffic monitoring location, like so a traffic roadside site. And we had sensors, which are shown in that top image, which are Earth Sense Zephyrs, deployed for a number of months, co-located with two different types of reference instruments for NO2. So specifically, we had a chemiluminescence instrument, which is a fairly standard and meets basically the regulatory requirements for their required monitoring that cities are doing. And then also a CAPS instrument, which has a much higher time resolution. So there are differences in the time resolution of these instruments. The Zephyrs, the small sensors, are at about 10 seconds. The CAPS is as high as 1 second measurements, and the chemiluminescence only has the highest time resolution is 5 minutes. And in the Zephyrs, we are looking at electrochemical cells for measuring that NO2. So first, we did a comparison of the two reference instruments to understand the differences there. And so maybe just as a bit of background, so the chemiluminescence instrument, it uses the reaction of nitrogen oxide with ozone to produce light that is in direct proportion to the NO concentration, which is quantified by a photodetector. And since NO2 does not directly produce this chemiluminescence, it needs to be converted to NO2. And so you have basically a two-step approach, which allows the detection of both NO and NO2 by sequentially measuring NO alone, and then NO with NO2 then being derived by subtraction. And the NO2 to NO reduction is basically done at high temperatures on the surface of a catalyst. This is relevant because this process can actually introduce interferences from other nitrogen-containing compounds like nitrates or ammonia. So you might actually be converting more than just NO2 to NO, and so it can lead to some overestimations of NO2. This is a known issue. This is not new. This is very well established, but it's just something to keep in mind. And so, owing to that method, that's also part of the reason that you have a 5-minute resolution as the highest resolution for this instrument. The CAPS instrument, in comparison, is basically it's a direct measurement of NO2 through light absorption at 450 nanometers. And so that's why part of the reason that you can get this 1 second resolution. So if we look at the plot on the left, that's comparing CAPS data to chemiluminescence data at 5-minute resolution. So the CAPS data has now been averaged to 5 minutes, and the colors are related to the standard deviation of the averaging of the CAPS data. And what you see is that the 5-minute averages that have quite high standard deviation, which means you have individual peaks of NO2 concentration that are quite extreme, which is possible due to, like maybe passing vehicle emissions or things like this, are where the chemiluminescence instrument starts to not perform very well. So basically these very short-term high peaks that are captured by the caps get lost in the chemiluminescence instrument because of the lower time resolution. What you can see in the plot on the right is that when you're looking at hourly data, which is how most air quality monitoring data is officially reported, that makes zero difference, right? The agreement between the instruments is excellent, and it's basically a 1:1. So here, just a further comparison, the solid line shows the caps versus the chemiluminescence for using 1 hour data, and the dashed line is 5-minute data. And so what you can already start to see here, the top plots show the R² value and the bottom plots show the relative percent error, is that there is a pattern, or is that there are things that influence the performance. And when you look at the hourly data, what you can see is something that looks a lot like an ozone concentration curve. So basically, there's the hypothesis that a lot of this is related to the chemistry that's happening in the atmosphere. If we then go on to look at the performance of the Zephyrs, these small sensors, compared to the caps and the chemiluminescence, and you look at the performance for the different averaging times, you can see that as the averaging times get higher or lower, I don't know, less, you see you go when you go from 10 seconds to like 1 hour or higher, the performance increases, right? So, and especially for the caps, there's basically a jump where 5 minutes you start to see some distinctly better performance. But 1 hour and above, it's, you're not gaining all that much. Here is basically the same thing. You're looking at R² values and relative percent error, but for 3 different sensors that were tested, with the time resolution decreasing, so going to lower time resolution as the colors get darker, right? So you have the higher performance as with lower, high, whatever, time resolution closer to 1 hour. And again, you see this pattern that you have performance dips basically during the middle of the day, right? So you see the performance dips basically between noon and 4. And you also see some weekday, weekend patterns. The patterns look very similar in the context of averaging with or calibrating with the chemiluminescence instrument. And so taking all that into account shows that, there is a difference in terms of how these sensors are being calibrated that will have an influence on the quality of the data and the error associated with the measurements. And this is something that needs to be considered. And basically, you can do measurements at quite high time resolution with these electrochemical sensors, but it's maybe not the best plan in terms of having very robust data. And so you can get decent performance if you are calibrating your sensors against something like a CAPS reference instrument, which also has very high time resolution available. If you want to use something like 5-minute data, but if the time resolution is less important, the reference instrument that you're using is also less important. So if you want to use hourly data, you're going to end up with similarly robust results with probably likely more similar and lower errors. So this obviously has implications for if we want to be using sensors like this for exposure studies or mobile measurements, because you can't really be looking at 5-second data or 10-second data unless you want it to only be like very indicative, because the error will probably be quite high. So I'm going to switch gears a little bit now and talk about how we applied, how we deployed some of these sensors. So I'm going to talk about two different policies that we evaluated. Both of them we were working with the city of Berlin, and or like district authorities. And so this first one is related to street space reallocation. And so the idea was that there was previously a road with 2 lanes of theoretically moving traffic and 1 lane of parked cars, and they reallocated the street space so you have 1 lane of moving traffic, 1 lane of parked cars, and a protected bike lane. So the bike lane is then protected through this lane of parked cars, whereas previously cyclists were riding in this street with the cars. And there was also a community space, which in the map is indicated by this green section. And this is basically where they closed it to cars, opened it to people, and 1 day a week, basically during the spring, summer, fall months, to allow it to be like a gathering space and a space for kids to play and social interaction to happen and things like this. And so we did measurements to evaluate both of these measures basically at the same time. We did stationary measurements and mobile measurements, and did measurements on the main street and then also on the side streets as basically a type of control. And then we also integrated the data from the Urban Background Monitoring Network to account for like changes in weather and in air pollution in the city in general, to isolate the signal from the policy. As with many things that we did around this time, the lockdowns kind of got in the middle of everything, but by using the urban background stations, we could kind of account for a lot of that influence. And yeah, okay, so because we talked about the stationary versus the mobile measurements and the implications, so in these cases, we are averaging over a quite like basically like the entire mobile route. So we're not looking at high time resolution data for these sensors. So in terms of the results, we were able to show that there was a reduction in NO2 exposure for the cyclist of about 22%. So looking at normalized NO2 concentrations, which means accounting for like the urban background and things like that. So just localized changes. And that we saw even larger reductions in the 95th percentile. And basically we saw no statistically significant change on the side streets, which would be an indication that this change in exposure for the cyclist was related to the fact that you're basically moving cyclists further away from the actual source of emissions, which would be vehicle exhaust or tailpipes. And the stationary sensors that we put up in like all along the route and in the area did not show the same change, right? So it's a very hyper localized influence that we were seeing. In terms of the community space, the change was a lot smaller, but it was still statistically significant, and there was not a statistically significant change in the control. So basically all other days where this space was not implemented. What was also interesting is that we did not see a similar effect in terms of a change in the particulate matter. So as I mentioned earlier, the sources of particulate matter have more sources, are less concentrated on one source in urban areas. And I think this also explains some of these results where we don't see the same kind of effect as we do for the NO2, which is very much dominated by vehicles. In this case, we also were working with a number of other groups to not only quantify the changes in terms of air quality, but also look at changes in cycling behavior in terms of user reactions and acceptance, and then also the political process that facilitated the implementation of these bike lanes. The second study is the pedestrianization of Friedrichstraße. So Friedrichstraße is a central road that's like kind of in a heavily touristed area in Berlin. And it was a similar approach to the one in the experiment that I just presented, except that we concentrated on stationary measurements and we didn't do any mobile measurements. So we installed sensors on lampposts in Friedrichstraße and on the two side streets where there was no pedestrianization that happened. And again, it was before and after measurements. And the measurements that we did with the small sensors were complemented by some reference measurements using this Luftrad or this air quality bike where we have reference instrumentation installed, as well as passive samplers that the city has been running for a bit, like over the longer term. This is a way of kind of like validating, again, some of these other measurements that we did. So what we found in this case is that if you compare the before versus the after, which is if we look at weekday, those are the ones that are circled. So the before is in red and the after is in blue. And these are, again, normalized concentrations to the urban background. And so what you see is that on Friedrichstraße, the street that was pedestrianized, you see a reduction in the NO2 concentrations. So they're basically now statistically similar to urban background concentrations, whereas before it was elevated and much more similar to something like a roadside location. Whereas on the two side streets, you don't really see any significant change in the concentrations. And this is also kind of interesting to us because we were thinking that you might even see an increase on the side streets of people who are trying to basically like drive around the pedestrian zone, but that also did not materialize, that increase on the side streets. And so just briefly, so these measurement campaigns that we did also had an influence on some of the political and societal discussions on these different mobility policies. And so this highlights some of the press that was related, in German, about the impact of these policies on air quality. And because of this transdisciplinary approach, our results were integrated into the final evaluation report that was put together by the city of Berlin. This is the one from the pedestrianized street. And so those results on air quality then get integrated into the decision-making process, which obviously also involves a lot of other factors, such as evaluations related to noise and traffic and different business considerations and things like that. And so while the air quality was a success, in this case specifically, the pedestrianization of this street ended up being very, very politicized. And I think decisions were made basically only on a political level, not necessarily taking into many of these things into account. But it was still, I mean, it's a very interesting process to be part of and see how things like this can influence or not influence depending on what the conditions are for work like this. In the case of Cottbus Dam, the bike lane was made permanent. So that's a different example. So, and yeah, we're continuing now to work with the city in other contexts where they're actually funding us to do similar evaluations of different types of mobility policies. Okay, so with the last a couple minutes here of my talk. I'm going to talk a little bit about Net for Cities. So Net for Cities is a 4-year Horizon Europe project that I coordinate. The full name being Real-Time Monitoring Networks and Transport Emissions for Tailored Zero Pollution Action Plans in European Cities. The project, it has a consortium of about 18 partners. The overall aim is to facilitate the realization of the EU Green Deal, their zero pollution action plans, with the main focus being on advancing air and noise pollution monitoring infrastructure. This is related to the new and emerging pollutants that I mentioned previously and the revision to the Ambient Air Quality Directive where this monitoring is going to be required. And then also hopefully providing an evidence-based support for implementing effective transport policies. So with the end goal of obviously improving air quality and mitigating noise pollution. So the broader context of this, as I briefly mentioned just now, is the revised air quality directive and the monitoring requirement. There's a very strong focus on transport in this project, which is related to the fact that there are objectives in the directive where they want monitoring at locations where high concentrations of, for example, ultrafine particles are expected to occur, in which they note sources from air, water, or road transport, such as airports, ports, and roads. And so that's a lot of where this call specifically was aimed at. And so what you can see in the map is our 11 partner cities and the different types of transport locations that we're going to be monitoring in those cities. And then there is also some targets in the zero pollution action plans related to reducing the number of premature deaths caused by air pollution by 55%, reducing ecosystems where air pollution threatens biodiversity, and reducing the share of people chronically disturbed by transport noise by 30%. And these are all like interim targets for 2030. In Net for Cities, it's basically like we're scaling up this transdisciplinary approach to work with our partner cities and other stakeholders. And so we set up the project so that the first year was aimed at basically just working with the local partners to identify policy interests and monitoring interests and logistics and things like that, where they could also influence some of the decisions on where this monitoring is happening in the cities, and also for the policy support, like are there specific policy measures where we could do specific measurement campaigns and things like this. And so obviously this is a transdisciplinary approach within a certain framework and boundaries, right? Because a lot of the outcomes or things that we have to meet are predetermined by the call, but there is obviously still some flexibility in how we implement these different things. And so the idea also was that through this transdisciplinary approach that, you know, with the monitoring instrumentation that we install and things like that, when we go through these different phases, that in the third phase, which is towards the end of the project, that there is a possibility that they have already been made aware of and are planning for in terms of uptake and continuity of these results. So taking on the monitoring equipment and continuing that for a longer time series, you know, using some of these tools that have been hopefully been co-developed over the course of the project, and making sure that there is some buy-in, and also that we're doing things that are more useful and might be taken up more readily because of the involvement of the cities and the stakeholders from the start. So just as a brief overview of some of the key activities, we're installing instrumentation on these new and emerging pollutants. So things like ultrafine particles, LDSA, which is lung depositable surface area, and is basically an alternative metric for measuring ultrafine particles in a way that is maybe a more health relevant metric. This is still something that's in development. Also looking at black carbon, ammonia, N2O, and some other greenhouse gases, as well as noise and traffic. There will be some remote sensing for individual vehicle emissions and quantifying emissions factors for both noise and air pollutants. I mentioned targeted campaigns to address specific policy questions or issues, and then further development of source apportionment approaches. So this is one example of what we're doing in Berlin, which is one of our partner cities. And so you can see the different types of instrumentation that we're installing. So there are typically 3 sites per city, and whether these are traffic or airport or port is determined by the cities and the capacity there. In Berlin, it's traffic locations and an airport location. We're installing UFP, monitoring capacity, as well as, did my slides go away for the sharing?
Yeah, the slides are gone, Erika.
Okay, hold on. Is it back?
Back.
Okay, sorry, my monitor just likes to disconnect sometimes. I don't know why. Anyway, so yeah, so you can see the instrumentation that we're installing to monitor these different pollutants. And then there's also the co-located noise and traffic, as well as some of the other activities that we're doing. So we're basically a year and a half in. And so we're basically done with the first phase, and a lot of the instrumentation was installed in basically the first and second quarter of this year. And so now we're starting to get data that's coming online. And the idea is that we have some planned outputs, such as recommendations for installing the monitoring capacity related to the new and emerging pollutants, recommendations for emission factors, updates to emissions inventories, but also, you know, some of these long-term data sets that can hopefully also then be used for different types of assessments. And we also have a real-time pollution dashboard where a lot of the monitoring that is happening that's online will be also then viewable in real time. So the last thing I'm going to show is, I think, like 2 slides on some of the very preliminary data. Like I said, most of this instrumentation came online in March or later. And so this is an example from some of the monitoring from Düsseldorf, which is done by our partners in Forschungszentrum Jülich. And so it shows the concentrations of ultrafine particles, as well as lung depositable surface area in blue, UFP in red, at the airport site and the urban traffic site. This is just a basic time series. And then here you can also see a diurnal cycle of these 2 parameters, where you can see that in general, you see a higher concentrations of ultrafine particles in LDSA at the traffic site compared to the airport site, and that the ultrafine particles have a slightly later peak than LDSA. They were also looking at comparing NO2 at the traffic site to the UFP on the left and the LDSA, and so you see there's basically a moderate correlation there. And so this is a very early results, and so there's a lot more to do. This is just like the first month or so of data, first couple months of data, and then hopefully with the longer term time series, we will be able to do a lot more and do some really interesting analysis. So yeah, this is just the final slide. So like I said, we're about a year and a half in. And so now we're very much in the data collection and starting to do analysis, as well as applying and developing some of these source apportionment techniques, planning the emissions testing, and starting to define some of these outputs with our stakeholders. So hopefully we will be able to provide some continuous measurements and things like that, and have uptake of some of this monitoring in the longer term. Okay, so with that, I would stop, and I'm happy to take any questions.
Thank you for such a wonderful talk. So, or any questions? If there's any question from the audience side, please, okay, question in the chat. It's a question from Ronak. Thank you so much for the excellent presentation. That's a comment. My name is Ronak Raj Sharma, and I'm a final year physics major student. Your data showed a clear trade-off between time resolution and data quality, with the 1 hour averaged NO2 data being much more reliable than the 5-minute data. Now, the question is, given this trade-off, how does it impact your discussions with policymakers? The first question. Is the high resolution 5-minute data still useful for certain applications, or is the more robust hourly data what becomes essential for creating policy relevant knowledge?
Yeah, so I think the main takeaway related to the averaging times and things like that is related to the error associated with the measurement, right? And so if you need to be able to say with certainty that you know, a certain policy created a specific, like, 2 micrograms per meter cube change in air quality, your errors are going to be much higher than that. But I don't, like, that's almost never the case. And so I think I'm not sure that I would necessarily say that it's like has a strong impact on the discussions with policymakers, because I think it's just a matter of making sure that you communicate these differences. And I think in most cases, what we're doing is quite like 1 hour hourly data is more than sufficient. I think it's more the implications that it has for, like, if you want to use sensors to look at personal exposure, because there, if you're moving through a city or changing environments, things like that happen quite fast often. And like maybe you walk through an indoor environment and you're only in it for a couple of minutes, and then you walk back outside or something like that. Like, that's going to be very hard to capture accurately using sensors like this. And so I think it's more of an application question. And I think the policy aspect is more just being able to communicate, you know, how robust the data is, what the associated uncertainty is, what conclusions you can draw from it, and what conclusions you can't.
Thank you very much, Erika. I hope, Ronak, you get your answer. Is there any more question?
I would have one. Can you hear me?
Yeah.
Okay.
Yes.
I missed part of the talk, unfortunately. I was in another meeting, but from what I've seen, it looks like a demonstrator you're implementing now, but do you think this will show some kind of a standard that future cities will have to develop, like monitoring of pollution at this range, or is this a demonstrator to show what can be done, and then some other cities can pick from that to see what is most effective in monitoring?
Are you referring to the work from Net for Cities? The
Yes.
monitoring of the new, yeah, okay. Yeah, so I mean, the idea is really with the revision to the air quality directive, cities are going to have to implement monitoring for things like ultrafine particles. And so a lot of what we're trying to do is in working with our partner cities is basically like give them a bit of a leg up, give them some experience with this install monitoring that they could either take over or not, but also try and have some lessons learned and some guidance from going through this process. Like, what are the key things to consider? Like, what are the potential pitfalls that you can maybe avoid if you think about XYZ beforehand, things like that. And so I will say it's definitely also been a learning process for us, especially trying to get all the monitoring instrumentation installed at 3 sites in 11 cities at the same time. But it's also been quite interesting. And I think, there's definitely things that we learned. For example, with the UFP, one of the big issues is that most CPCs need butanol, and most cities want nothing to do with butanol because it can influence and interfere with other types of measurements. And there is an alternate fluid that our partner Air Modus uses, propylene glycol, where we're basically working on showing equivalence because it's far less toxic. It doesn't have an interference with other types of measurements. And so the idea is like, okay, can we use things like this to show that this is an equivalence and still meets the SEN standards, and, then have this as, guidance or basically lessons learned that can be communicated more broadly when other cities are starting to implement this type of monitoring.
Okay, yeah, thanks. Interesting.
Thanks, Arno.
Any more questions? Erika, there is one question of mine. Whenever we do the experiments and then we got the result, and then we, want to implement at the ground level, that is at the policy level, that what challenges maybe the scientist would face from the experimental side and then to the policy implementation, and how can we as a scientist, basically convince the government that they should, implement the urban greening or the smart city planning in that way in which we are doing, because that's the biggest challenge in the developing countries, because in developing countries there is a set format of plantation and all. So how what are the ways, or what are the things, or what are the points should we highlight so that the government can care about the scientist view? I know it's a different question, but it's just a curiosity because I'm doing some kind of work and facing some challenges. So
Yeah, I mean, I think, well, so one thing I can say is this idea of like, I'm going to measure all these things and tell you this is effective and this is not, and, therefore you should implement X, is not going to be effective, right? I mean, I think we're all aware that the deficit model, you just have more knowledge, therefore you will make the right decisions, is not true. I mean, I think in general, like, if any of us look at like our eating patterns or things like that, like obviously everybody knows that if you eat healthy food, that's better for you and you'll be healthier. That stops basically almost no one from eating things like cake, right? So more knowledge does not equal better decisions. And I think that's one of the things where, if we're using something like a transdisciplinary approach, it can help make sure that the right questions are asked, or that the research is designed in a way that can be useful, right? Because I have also had conversations with policymakers where they told me about, for example, a citizen science network that was implemented in a city, and then there was they basically had an event at the end, and they were like, look, we've generated all this awesome data about X, Y, and Z related to this, and isn't this awesome? And they were like, well, no, not really, because we can't do anything with that in that way that it's done. Like if we had talked about it at the beginning, then maybe, but now, like, no. And so I think, that's not always the case, right? There's definitely ways that you can also design things and do them, and they will be quite relevant. But I think, something like working with policymakers from the beginning can ensure that, things that we maybe find scientifically interesting, you can also find synergies with where the policy is, and maybe I think the involvement of the stakeholders from the beginning also results in more buy-in, right? Like they feel like they have more ownership of the process, more ownership of the results, which also makes them more likely to use them and consider the results. And so I think that's one aspect of it. It's not always possible. And the thing is in any policy process, science is one input of many, right? And like in one of the examples that I gave, like there was a bunch of input, and basically it turned into like a political topic that was basically a power play. And so at that point, none of those inputs matter, right? But I think, involving people can increase buy-in and can increase the strength of the science in these debates, and just being present. But it's also, it takes time to build some of these relationships, and it's also establishing trust and things like that. But I think it can have quite positive impacts if you have the time to build the relationships and go through processes like that. Yeah. I hope that kind of answered.
I will try to convince happen. The next question from our ECR iLEAPS, Saurabh Sonwal. Have incorporated the approach in the study. So what to suggest to EERs who are being discipline and air quality? The potential approach or key things that need to consider when you are working to test any policy at local or national air quality with DD approach.
Yeah. So a number of years ago, we actually wrote an article about I'm going to butcher the title, something like prepare scientists to engage in science policy. And there was some of the key things that we kind of outlined or thought were quite important. And a lot of it's related to kind of like science communication skills and understanding something about the policy cycle and windows of opportunity and things like this. And so I think that there are skills that you can work on and things that you can develop to improve your potential or improve your skills in science policy and being able to work in a transdisciplinary environment and things like that. Beyond that, I think a lot of it is relationship building and doing good science, to really show what is, where the potential is and things that you can contribute. And I think that's a lot of it. Anyway.
I hope so. With your answer. Thanks, Erika. Is any more question? So I don't see any more question. Thank you very much, Erika, for taking time out from your busy schedule and